Introduced. Okay, so I'll be talking about testing distribution families, and I believe it's a very fundamental statistical question. I'll try to state it in the simplest of terms, and we'll try to look at it from a sample efficiency and computational efficiency point of view. And this is joint work with Kostas Daskalakis and Gautam Kamath, and this is the least happy picture of him I could find on the internet, probably with the least number of teeth showing. So what's the problem of property testing? Okay, so there is an object P which could be a graph, it could be a probability distribution, it could be an image, and we have a certain hypothesis about this object. For example, if it's a graph, is it a bipartite graph? Or if it's a distribution, is it a binomial distribution? And we want to answer these questions, and the way we access this object is through this, there's a curtain between the object and us, and we see some kind of function of this object, some randomized function. For example, if it's a distribution, we probably get random samples from it. If it's a large graph, we probably see edges one by one. And we want to answer these questions with the fewest queries possible and in the fastest possible computation time. So if we go to the problem of testing distribution families, here we have the hypothesis H, and let PH denote the class of all distributions that satisfy our hypothesis. And we observe x1, x2, and so on independently from an unknown distribution P. So P is some unknown distribution. It may or may not be in our hypothesis class. And our objective is to answer precisely the question whether it is in the class or it's far from all distributions in our hypothesis. So pictorially, this is the class of our hypothesis, and we want to answer if it's here or here, and we don't care about what happens in between. Is the setup clear?
Distance?
So the distance we will be concerning in this talk is mostly the L1 distance or the total variation, and this is just for simplicity of pictures. The hypothesis class need not be even a convex set in the simplex. So there has been extensive work in statistics and information theory. Primarily, when we say composite hypothesis testing, you have two families of distributions and you just want to distinguish them. And most of the work has focused on the asymptotics, where you have some distributions over fixed alphabets and you let the sample size grow to infinity. So we want to answer the question in the different setup, where we look at how many samples you need and how fast you can solve this problem. So when we look at the problem of testing, the natural question that comes up is learning. You want to learn a distribution that satisfies a certain hypothesis. And this has a large literature in both the setups, both in statistics and it has gained a lot of interest recently in theoretical computer science, where you want to characterize the sample complexity of estimating classes of distributions. For example, if you have a mixture of Gaussians, this has been very well studied over the past decade or so. However, when we go to the problem of testing families of distribution, there are very few results that are known, which is a little disappointing. And if we go to the two results that are actually known, one is testing identity, in which case our hypothesis consists of just one distribution. So it's a single distribution that is known to us, and we want to test if we are getting samples from that distribution. And the other class is testing for monotonicity when the distribution is over some ordered set. So we'll go into details on these two problems. So is the setup clear? Okay, so what's the problem of testing identity? You have a single distribution, Q0, that you know, over an alphabet of size k, and you want to distinguish between these two classes. So when Q0 is a uniform distribution, the problem was studied by Paninsky in this small sample regime when you get much fewer samples than the domain size. And only recently the problem was solved entirely when the sample complexity and the time complexity were shown to grow at square root of the size of the domain and inversely proportional to the square of the accuracy that we want, or the error parameter. And the other results, okay, before we go to the other results, So testing identity implies that we have a we know the hypothesis that we want. So in other words, we know the exact description of the distribution. However, it's much more natural, and it's pretty surprising that that was not the question that was first proposed, that you want to test against a family instead of knowing an exact distribution. For example, as Professor Olitsky says, there is nothing called as a uniform distribution. Everything could be close to uniform, but there is nothing that's entirely uniform. So we want to test against families of distribution instead of... We want to test against families. Yes. So the other problem that was studied was testing monotonicity by Batu, Kumar, and Rubinfeld, who showed that, again, the number of samples grows as square root of the domain size times some polylogarithmic factor, 10 should be k, and as 1 over epsilon to the 4 in terms of the error parameter. Moreover, there is a lower bound of square root k over epsilon square. And even for the simplest of problems, we still do not know what the correct answer is in terms of epsilon, which is slightly sad. So this is going to be the agenda of the talk. We'll try to motivate. If all this motivation was not enough, we'll try to motivate it with an example of life and death. And then we'll provide our general algorithm and talk about 2 classes of distributions for which we have optimal algorithms. And then we'll sketch a proof for one of them. So there is an epidemic. There are so many epidemics going on. So let's say take any one of them. And our hypothesis is there is a single source of the disease. And the probability of infection reduces as the distance from the source grows. For example, this picture illustrates it, and this is the probability of infection. So this problem will correspond to testing unimodality in R-square when you observe a bunch of samples and you want to see if there is a unimodal distribution that conforms to your observations. However, this problem of unimodality will not follow strictly from the problem of monotonicity that we studied before. And I'll come back to that if time permits. So let's go back to our problem. The setup is this. You have a class of distributions. You want to test if a distribution, if given samples, a distribution belongs to the class or is epsilon far from all of it. So what could be the simplest approach? You try to learn the distribution assuming it's in the class. So that's the first step you do. So you take a few samples from the distribution and you approximate it with a distribution that belongs to the class. So PH is the class. For example, if you want to, if your class is the set of all Gaussians, once you observe the samples, you probably estimate it with the mean and variance, and you take that Gaussian as your starting point. So that's the Q you have. Now, in the framework we are studying, if the distribution was not in the class, then the L1 distance between the underlying distribution and what you estimated has to be epsilon. However, if the distribution belongs to the class, suppose we have a learning algorithm that can learn it very fast, and let's say you can get up to an accuracy of epsilon over 2. Then the problem reduces to the following. In the next step, you have to test whether an unknown distribution P to which you have a sample access is epsilon over 2 close or epsilon far from a known distribution. Now you have the complete description of the distribution Q. Sadly, the optimal sample complexity of this problem is far from being optimal for testing the entire family of distributions. Namely, if you want to just solve this problem, the number of samples required is linear in terms of the support size of Q. Which is equivalent to learning an arbitrary distribution. So what our approach is going to be, and that's what we'll describe in a nutshell, it starts with the same approach. We try to properly learn the distribution, assuming it's in the class. And as before, if the distribution does not belong to the class, we are at least epsilon far from what we have learned. And if the distribution is in the class, we try to approximate it to a high accuracy, let's say epsilon squared, by taking as many samples as required depending on the complexity of the class. And in the next step, instead of doing an L1 testing algorithm, we do an L2 test. and which suffices for the classes that we'll consider. So that's the entire algorithm, and we'll show that this approach is actually nearly optimal for two broad classes of distributions. Any questions?
What do you mean estimate P with a Q?
So you are given samples. You assume that your underlying distribution is in the class, and then try to find a distribution that's close to that is closest to these observed samples. So you start with some algorithm. Let's say an oracle gives you an algorithm. So that may be a critical step, because for many classes of distributions, it's not even known how to solve this problem efficiently. For example, mixture of Gaussians. So here are two classes that we'll consider. One is Poisson binomial. So what are Poisson binomials? So it's a sum of independent but not necessarily identical Bernoulli random variables. For example, the attendance here, suppose everyone had a coin with them, which they toss and then decide whether to come to the talk or just have coffee outside, independent of the others. So in such a case, such a distribution is called Poisson binomial, and there has been a lot of work in probability theory to understand Poisson binomials, mostly in the context of seeing how fast they converge to Poisson distributions. And more recently, this was studied in the context of anonymous approximating the Nash equilibria of anonymous games by Daskalakis and Papadimitriou. And in another work, Daskalakis, Diakonikolas, and Servadios looked at the sample and time complexity of estimating of learning Poisson binomials. And the second class that we'll consider is the class of log concave distributions, which, as the name suggests, if you take log of the probability values, it's concave. And there are a large class of discrete distributions that are log concave. These are a few examples. Poisson could be added to it. And similarly, a large class of continuous distributions are also log concave, and they appear in the context of rejection sampling. So there has been a lot of recent work on studying the rates of convergence of estimators for log concave distributions, and slightly disappointing that for discrete log concave distributions, I couldn't find any results that are independent of the alphabet size. So most of the results that I could find, namely in this last one, they try to study the rate of convergence of maximum likelihood estimator when you fix the distribution and let n grow. Whereas I believe it's possible to characterize the rate of convergence independent of the support size for the class of log concave distributions. So these are the results that we have. So for the class of Poisson binomial distributions, the number of samples required to test grows as the alphabet size to the 1/4 over epsilon squared, plus a number of samples that's independent of the domain size. And it runs in time that's linear in the number of samples that we take. Similarly, for the problem of log concave distributions, it goes as square root k, and the time is again efficient in the alphabet size. Moreover, we can also show lower bounds of that match in terms of k and epsilon squared, and is off by only a logarithmic factor in epsilon. So recently we were made aware of results by Canon, Diakonikolas, Goliakis, and Rubinfeld, who come up with a very generic algorithm for testing all of these problems, all of these families, namely monotone, unimodal, and so on. And another nice thing about their approach is it works for even mixtures of distributions. However, the sad thing is it's computationally intensive. And as we can see, for the class of log concave distributions over k elements, the time you require is k over epsilon to the k, compared to, let's say, k cubed that we have. And okay. Yes.
Remember, even for estimating the log concave discrete distributions,
it's very easy.
Is alphabet size independent? Right?
Yes, it's very easy to estimate, but it's not easy to test. That's correct.
can you just estimate and declare to the nearest log concave?
But that's not the problem, right? What if your distribution is not a log concave distribution? You estimate it, then the problem comes in. And that's why, so we'll go through the test statistic once. So the sample complexity and everything, all the sample complexity comes from the variance computation, not from the mean computation of the statistic. That's one of the things we'll talk about. So let's walk through the result. Okay, so you want to estimate a log concave distribution, and this is the algorithm that we propose to properly learn it. So what is properly learning? You want to output another log concave distribution instead of outputting just any density. So you start with a piecewise linear estimate of the distribution, and it's known that if your underlying distribution is log concave, you can obtain a piecewise linear estimate of it. So you start with it, and then you solve the following LP, which is nothing but, it characterizes two things. This is the condition of log concavity, and this says that you try to obtain multiplicative estimate of the probability value at each point. And if you obtain a multiplicative estimate of the probability at each point, that will convert to an upper bound on the L1 distance between the distributions. So we solve this LP and show the feasibility of the underlying distribution for these two conditions. And this also gives a proper learning algorithm for log concave distributions that's independent of the alphabet size.
So what's the objective function in the LP?
There is no objective. There's just a feasibility, just for feasibility. So if this is satisfied, then you are close in multiplicative with whatever you have estimated, and therefore you are at most epsilon far from the underlying distribution. Yes. Now we go to the testing phase. We have learned a log concave distribution. How do we test against it? So let Ni denote the number of times symbol I appears when you have sampled n times. And this is the test statistic. Okay, let's not worry what it is. Let's just look at its expected value. Its expected value will be just the squared L2 distance between P and the underlying distribution. This is just the computation of mean and variance of binomial distributions. And once we do it, we have to analyze what happens in the two cases when the distribution is in the class and is far. When the underlying distribution is not in the class, by definition it's epsilon far from what we have learned, and therefore we use the most powerful inequality known to us, it's the Cauchy-Schwarz inequality, to lower bound the expected value of our test statistic, of the test statistic. Namely, it will be just the L1 squared over the effective alphabet size. So I won't explain what k epsilon is. It's the L1 squared over the number of elements that we are summing over. If the distribution is in the class, then we try to learn it much better. This Q should be PLCD, such that the L1 distance is at most epsilon squared, and then we show, depending on the class, at least here, then we show that the L2 distance is at most epsilon squared over, should be k epsilon. So we can show that in fact, with a constant number of samples, the test statistics start diverging, the expected values. However, when we look at the variance, it can be shown that we require at least square root k over epsilon squared samples in order for concentration to take effect. So we have these two. We have the test statistic T. We try to analyze its mean and show that it's different in the two cases, and then we look at the variance and show concentration when the number of samples grows beyond square root k over epsilon squared. So these computations are slightly tedious but pretty straightforward. And the lower bound is the general machinery of Fano's inequality. This should be happy news. So in summary, we are trying to motivate this problem of testing families of distributions in the setup when you have very few samples and you are computationally bounded. And as a corollary, we have also proved, given a proper learning algorithm for log concave distributions and optimal testing for the classes of log concave and Poisson binomials. So in future, one would like to characterize the complexity of testing classes of distributions that are parameterized by some parameters, and also design efficient algorithms for this task. Thank you. Yes.
Where's your last line?
Thank you. That's all.
You showed some sample complexity lower bounds, right?
Yes.
Do you also have time complexity lower bounds, and in general, is there a trade-off between?
So there are no time complexity. I mean, there are some, not in this framework, no. And here, I'm not sure whether there will be, because the gap is so small that perhaps there is an algorithm that will work. Maybe just that the problem with most of the algorithms that require more samples is they divide the data into certain regions and then they take sort of a union bound. The way we are looking at it is looking at the whole distribution as a whole, and I believe it might be possible, at least for monotone distributions, to do the same.
So, any other questions?